Okay, welcome to Robotics 1. In today's class, we will talk about forward and inverse kinematics. So, today's lecture is lecture 4, right? So lecture 4. And we'll talk about forward and inverse kinematics. So let me start with a very simple example, almost a trivial example that we looked at when we started looking for forward and inverse kinematics. So to my online students, please mute yourself because otherwise that means whatever you say gets recorded. Anyway, so in the case of forward and inverse kinematics, the definition of forward kinematics is given the joint values, find end effector position. EE stands for the end effector position and orientation. So for an example, you are going to have, say, joint theta 1. That's joint number 2 has theta 2. Joint number 3 is, say, theta 3. We would substitute theta 1, theta 2, theta 3, and we should be able to get Px, Py, and Pz. These are the positions of the end effector. Now, the forward dynamics problem is unique, which means for the values of theta 1, theta 2, theta 3, there will be one and only one Px, Py, Pz. In the case of inverse kinematics, the problem is posed the opposite way. Given end effector position, find theta 1 or find joint values. Find joint values. Joint values. So which means given the value of Px, Py, and Pz, find the values of theta 1, theta 2, and theta 3. Now this is an interesting problem because for a given value of Px, Py, and Pz, you may have no solution, you may have multiple solutions, or you could have just a singular solution. So what that means is here you can have a no solution. So which means, for example, this Px, Py, Pz is outside the reach of the robot. So if you have a robot arm, the maximum reach of the robot arm is here, but your Px, Py, and Pz is outside the work envelope of the robot. So clearly, no amount of calculation will get you that result. Sometimes there could be multiple solutions. So a very common example is, so multiple or say unique. So think about that we have a robot arm, and this is the same robot arm that we talked about in the very first class. So this is the robot arm, and what you have is, I give you, say, this is my datum, and I give you a value of px, and I give you a value of py. So px is this distance, and this px is always defined with respect to the zeroth or the inertial frame. So this is going to be my zeroth frame or inertial or fixed frame. So I will call this x0, y0, and z0 is coming towards you. And then what I have here is this distance is py. So we have px and py. Now, if I were to use the same sign convention that we used earlier, if I were to use the same sign convention I used earlier, if I say this is my theta 1, and I'm going to set up this problem, but I want you to understand the sign convention I'm going to use to set up this problem is slightly different than we will use to set up the three-dimensional problem. So I'm not going to solve this problem, but I would just set it up so that it's easier to understand. So for an example, this is theta 1, and then this is theta 2. I'm given, so the inverse problem is, so let's start with the forward problem. Forward problem is theta 1 and theta 2 are known, and find out px and py. No problem with that. This problem, forward problem, can be solved. Now the inverse problem is px and py is given, and I need to find out theta 1 and theta 2. Please understand, the equations that we are going to use, they are going to be the exact same thing. So for an example, let me set up this problem. If you remember, the forward kinematics equation, we wrote something like px is equal to, this was L1, this was L2, L1 cosine theta 1 plus L2 cosine theta 2, and py in this particular case is going to be L1 sine theta 1. And please understand, here I need to use minus L2 sine theta 2. Everyone understood this? Yeah. Now the question is, if I give you the values of theta 1 and theta 2, it's very easy to find out px and py. But now let's try to understand how this problem can be attempted if I were to go in the reverse direction, which means I give you value of px, I give you value of py, and which means the left-hand side of this equation is known. And let me give you some values. Say px is 100. 100 is equal to, say, L1. I'm going to give you, say, maybe 50 cosine theta 1. And L2, I would say again 50 plus L2 cosine theta 2. And then I will give you the value of py. And clearly, if so, let me give you some L2, which is say 60. And I give you value of py as, say, 25 is equal to 50 sine theta 1 minus 60 sine theta 2. Now, some of you may say, oh, two equations, two unknowns, right? This is again two equations and two unknowns. We should be able to solve this problem, right? But the solution is not easy, because please try to understand the relationship is given in terms of trigonometric identities. So if you want to solve this problem, you need to convert sines and cosine into something that can be added and easily solved. What I mean by that is, let me use the brute force approach, saying that I'm going to write this as a matrix. So something like this. So 50, 60, 50, minus 60. But recognize, if I try to do it like this, I don't have a vector to represent. What that means is I cannot use any algebraic manipulation or simple linear algebra to solve this problem. The trick that is used here is something like this. And I'm going to tell you the trick, but there is an easier way of solving this problem. So I would convert using the half angle formulae. I would convert cosine theta 1 into its tangent component. So it will be like tan of theta 1 by 2, something like that. I would convert sine again into tan of theta 1 by 2. I would convert, so what would happen is, once I convert those equations into tan, I would be only left with 50, some constant multiplied by tan theta 1, or a fraction of tan theta 1, tan theta 2, tan theta 1, and again tan theta 2. Do you agree with me? At that point, what I could do is I can grab tan theta 1 or tan theta 1 by 2 and tan theta 2 over here, and I can independently solve those equations. Everyone understood this? This is the standard technique that is used when you are trying to solve the inverse kinematics problem. But again, what I want to tell you is, if you look at the textbook, he will talk about 2 or 3 tricks, like you need to substitute or you need to square and add. So basically what you do is you square the first equation. So let me show you these techniques. So basically convert cosine theta 1 into a fraction of tan theta 1. Then change sine theta 1 into a fraction of tan theta 1. And depending upon what trig identity you use, you will get, but you'll convert those into tan. So it could be like tan theta 1 by 2 or tan 2 theta 1, whatever identity you use. Same thing is going to happen with cosine theta 2. That will get converted into some algebraic equation involving tan theta 2. Sine theta 2 get converted into some algebraic equation involving tan theta 2. After you substitute, this equation will only contain tan theta 1 and tan theta 2. And when I say tan theta 1 and tan theta 2, depending upon the substitution, it could be tan theta 1 by 2 or tan 2 theta, whatever substitution you use. So this is one approach. Okay, this is one approach. The second approach is, and to be honest with you, we are not going to use these approaches, because these approaches are very much dependent on the way the problem is set up, which means some problems are easier to solve with the tangent substitution. Some problems are easier to solve with a sine cosine manipulation, and I'll show that to you. So second manipulation that is possible is I'm going to use this equation 100 minus 50 cosine theta 1 is equal to 60 cosine theta 2. I would use 25 minus 50 sine theta 1 is equal to minus 60 tan, minus 60 sine theta 2. Sine theta 2. And the most natural thing to do at this point is basically square and add. And what happens when we square and add? Once we square and add, I don't know if you follow this completely. The step is, so basically I would square this, I would square this, I would square this, I would square this, and then add these. As soon as I perform this addition, I want you to notice the final answer is going to look a long answer, but I want you to understand what simplification is going to happen. Cosine square theta 2 square can be added to sine square theta 2, which means these two quantities after squaring and add becomes 1. Same thing is going to happen here. So this 50 cosine theta 1 square will get added with 50 sine theta 1 square, and this again cosine theta 1 square plus sine theta 1 square is going to give you 1. There will be one term which will be the product of these two multiplied by 2 cosine theta 1, product of these two multiplied by 2 multiplied by sine theta 1. But recognize that expression is going to have only theta 1, which means after you simplify everything, what's going to happen is you are going to get tan of theta 1 is equal to some expression. Once again, I repeat. And again, you are welcome to do this, but I'm not going to do this because this method, in my personal opinion, is too restrictive to certain problems. Like this method will not work for all problems. That method is not going to work for all problems. You have to use some combination method to solve inverse kinematics problems. And I don't like that. I just want one method that will solve all inverse kinematics problems, whether the problems have one solution, two solutions, no solutions, multiple solutions. And here, what is happening is, once again, once you square and add, theta 2 gets eliminated from the expression, and your entire expression is only in the form of theta 1. There will be a sine theta 1, there will be a cosine theta 1. And once you combine everything, what you can do is you can just divide, and then you will get a nice expression for tan theta 1, and that will give you the answer. Everyone understood this? So this is method 2. Third method is like you use some type of a geometric approach. What do I mean by sort of a geometric approach? So you look at the geometry of that kinematic diagram or that figure and see like, hey, can I use some type of a geometry relationship to make my life easy? So perhaps you can express a relationship between the sine theta 1 and sine theta 2, and somehow make that substitution in the very first equation and try to solve. So the third approach, which is commonly used, is geometric approach. So this is the third approach. So if you look at the textbook, all these three approaches are discussed in detail. But here is my hesitation about these approaches. Like that's too specific. So for an example, if and sometimes what you have to do is you have to use your creative mind to make some simplifications. I mean, not one substitution is going to solve all the problems. So the best way, I mean, when I studied the robotics for the first time, I had to run all the trig identities. I had to remember those. I had to look at some geometric substitutions, some series expansion, and so on, and some approximate techniques to solve this. But nowadays, what you can do is you can just program this equation inside MATLAB, and MATLAB will give you all the solutions. And that's how it is done in industry. Nobody would solve this equation by hand. Why? Here is the problem. Because please understand, this problem, if I use this approach, I would get a value of theta 1 and I would get a value of theta 2. But please understand, when I'm trying to solve the inverse kinematics solution, this is a valid solution. So this is a valid solution. At the same time, this is also a valid solution. So, and these angles are going to be different. So you have L1, you have L2. So the same position can be met by a different combination of angles that this approach does not provide. And many a times, your actuators or your motors, they will have physical limitations. Like the motor cannot reach that angle. So you have to look at the alternate possible solution. So inverse kinematics, using either the geometric approach or using the trig identities, you have to be extra careful. You have to use something called as A tan 2, which is arc tangent, to find all possible solutions. And clearly, if you are going to do arctan, you are going to use a calculator and all that stuff. So the inverse kinematics, if you look at the textbook, there's an entire chapter on inverse kinematics, and all that chapter does is talking about technique 1, technique 2, and technique 3. But what I want to do is, in today's class, I want to work out a forward kinematics problem. We'll program that problem inside the MATLAB. And then what I want to do is I want to use the MATLAB again to compute the inverse kinematic solution. What is the significant advantage of that? The advantage of that is MATLAB will do all the heavy lifting for you. MATLAB would use the numerical techniques, shooting approaches, and give you all possible solutions in nice combination, where you can write a program that will look at the actuator limits, that will look at those joint values and select the most possible or most probable or sort of most optimal solution to achieve that end effector position. Everyone understood this? So these approaches are good to know, but practically we would use MATLAB. Everyone understood this? So now what I'm going to do is I'm going to work out a simple problem. And let me tell you, this is the problem that I'm going to solve. This is very important. It's the same problem in your assignment 3. So please pay attention. But in assignment 3, actually, there is an activity where I want you to build a cardboard robot arm and do the forward and inverse kinematics. So you do the hard part, like building the arm. I will do the easy part, solving the equations. Okay, so this is now. Let me tell you, this problem is similar to the problem that we discussed in last class, but instead of 2 joints, now it has 3 joints. And next part is this. So let me tell you a philosophical approach in solving articulated robots. If you want to achieve X, Y, Z position, and roll, pitch, and yaw orientation, there are 6 variables. So px, py, pz, theta, psi, and phi. So these are the end effector orientations. So typically, if you want to build an articulated robot that can give you this 6 degrees of freedom solution, it needs to have 6 independent joints. So which means you would have theta 1, theta 2, theta 3, theta 4, theta 5, theta 6, and this 6 degree of freedom robot will give you the wrist or the end effector position and orientation. Everyone understood this? If you decide to solve the forward kinematics problem for this 6 degree of freedom robot, no problem. Substitute the values of theta 1, theta 2, theta 3 all the way to theta 6, and you'll get px, py, pz, roll, pitch, and yaw. However, if you substitute px, py, pz, roll, pitch, and yaw, and try to compute thetas 1 to 6, it will never work. What it means is for a 6 degree of freedom actuator, inverse kinematic solution is not possible for all the cases. So here is the trick. How do we eat an elephant? In pieces. So what it means is if you have this 6 degree of freedom robot, separate this out into first 3 degrees of freedom and then next 3 degrees of freedom. The assumption is joint theta 1, theta 2, and theta 3 are responsible for px, py, pz. Joint 4, 5, and 6 are responsible for roll, pitch, and yaw. And then you will get a very clean solution. Everyone understood this? So if you have any robot that is more than 3 degrees of freedom, the best way to solve this is sort of cut it into pieces of 3 degrees of freedom each. Only then you will be able to solve. So I will solve the 6 degree of freedom robot in next class. But I want you to understand that if you have a 6 degree of freedom robot, you can even MATLAB will not be able to give you the solution for all thetas given 6 variable unknowns. So what you need to do is you need to split it. You need to split the first part, which is articulated robot, and the last 3 degrees of freedom, that is called as the spherical wrist. So what I'm going to do is in today's class, I'm going to solve the first 3 joints. So let me set up the problem. So we have a robot, and I'm going to draw the kinematic diagram for this robot. By the way, everyone remembers the rules? Okay, good. So this robot has the first joint, which is the revolute joint. Then there is the second joint. This is against the revolute joint. And then there is one more joint. And then at the end, there is this end effector. So this is first revolute joint. This is the second revolute joint. This is the third revolute joint. The first revolute joint is perpendicular to second revolute joint. It is the second revolute joint is parallel to the third revolute joint. So this is an R type of robot. Everyone understood this? Now I need to set up the coordinate system. So Z axis must pass through the joint. Z1, Z2, and this joint doesn't matter, but we will go step by step. Then I'm gonna call this one as X naught. Now my X1 has to be perpendicular to Z1 and Z0. So this is going to be X1. And then I'm gonna have my X2. And a different color pen. This is going to be my X2, like this. Does everyone remember the rule, or do you want me to write it down? Anyone who does not remember the rule, write it down. Okay. So rule number one, don't forget all the rules. Rule number one, Z passes through joint. Second, Xn intersects. Actually, Xn has to be perpendicular. Xn perpendicular to Zn and intersects Zn minus 1. And then right hand coordinate system. So X0. So now I have Z going up. So my Y needs to go out. So now here, Z is coming out, X is going like this. So my Y, something has to be like this. Z2, X2, my Y2 has to be something like this. And this is the end effector. There is no joint or anything, but for the sake of simplicity, I'm going to assume the same coordinate system as the previous one. So this is going to be X3, Y3, Z3. Everyone okay with the coordinate system? Right hand coordinate system, curl your fingers. Thumb should point in the positive Z direction. So which means my theta 1 should be like this. My theta 2 should be like this. And my theta 3 should be like this. Any questions here? Please note, luckily for this problem, there are no exceptions to the rules. But once we are comfortable solving the forward and inverse kinematics problem, I will take the problems where there are exceptions to these rules and we have to add intermediate frames so that the rules can be satisfied. So look something like this. The 0th frame is the inertial frame. So what I'm going to do is, I'll use this here, 0R1 cosine theta 1 sine theta 1 sine theta 1 cosine theta 1 0 0 0 0 1. Are you with me? What am I missing here? I'm missing the projection matrix. Super duper important. Well, how do I determine the projection matrix? Projection of x1, y1, z1 onto x0, y0, z0, right? So x1, can you see x1 is in the same direction as x0? So 1, 0, 0. Y1 is in the same direction as Z0. So basically 0, 0, 1. And Z1 is in the opposite direction of Y0. Do you agree with me? So 0, -1, 0. Do you agree with me? which means my final rotation transformation, please note, this is the correct rotation transformation, okay? Because the rotation transformation should have the information about the axis rotation. Also, it should relate the transformation between the axes. So my rotation transformation, first row, first column, cosine theta 1, first row, second column, first row, third column, first row, first column, first row, second column. So basically this becomes sine theta 1, second row, second column, second row, third column, first row, first column, first row, second column, third row, third column. So this is my correct rotation transformation, and this needs to go in homogeneous transformation. So next thing is find the homogeneous transformation 0h1. 0h1 will contain the rotation matrix 0 cosine theta 1 0 1 0 0 0 0 and finally 1. And here once again the position of frame 1 with respect to frame 0 in the coordinate frame of frame 0. And I will write this down here once again. Frame 1 with respect to frame 0 in x0, y0, and z0. So what that means is, let me give you some dimensions. So this dimension, I'm going to give you A1. This dimension, I'm going to give you A2. And this last dimension, I'm going to give you A3. So can you see, and this relationship should be valid no matter what the angles are. So whether theta 1 is 0, theta 1 is 90, theta 1 is 360, theta 1 is 270, it should be valid. So can someone tell me what would be the location of frame 2 with frame 1 with respect to frame 0 around about x0? 0. Location of frame 1 with respect to frame 0 around y0. Location of frame 1, so this is frame 1, this is frame 0, about z0, which is a1. Are you with me so far? And this is positive because we are going in the same direction as z0. That's why this is positive, not negative. Okay, so 0h1 is found out. The next step is 1r2. 1r2 again will be cosine theta 2 minus sine theta 2, sine theta 2, cosine theta 2, 0, 0, 0, 0, 1. This is the same matrix that we use all the time. So, however, let's talk about the projection matrix. And the projection matrix is going to be here x2, y2, z2, x1, y1, z1. So x2 is in the same direction as x1. Can you see x2 is in the same direction as x1? y2 is in the same direction as y1. And z2 is in the same direction as z1. Are you with me so far? So what I have here is I have an identity matrix. So if you multiply any matrix by an identity matrix, you just get the same matrix. So which means I'm ready to go for 0h2. 1h2. And 1h2 is going to look like, since it's the multiplication by identity matrix, cosine theta 2 minus sine theta 2, 0, sine theta 2, cosine theta 2, 0, 0, 0, 1, 0, 0, 0. And then there will be 1 here. And now what I want is, once again, let me explain this a little bit carefully. This is frame 2. Location of frame 2 with respect to frame 1 about x1 for all possible values of theta 2. They are a2 cosine theta 2. a2 cosine theta 2. Why? Because in this kinematic diagram, I have shown my theta 2 is equal to 0. That's why the distance is a2. But theta 2 could be 10 degrees, 15 degrees, 20 degrees, 100 degrees, 180 degrees. So next is going to be a2 sine theta 2. And there is no z difference. So 0. Are you with me so far? Last, same technique, 2r3. And this goes like cosine theta 3 minus sine theta 3, sine theta 3, cosine theta 3, 0, 0, 0, 0, 1. And this is sort of trivial, but still I will do it, okay? So this is going to be like x3. Why x3? Because 3 is here. x2, y2, z2, x3, y3, z3. Now please understand, x3, y3, and z3, they align with z2, x2, and y2. Do you agree with me? So that means that matrix has to be identity. Everyone understood this? x3 is aligned with x2. So I'm going to have this exact same matrix here. So 1, 0, 0, 0, 1, 0, 0, 0, 1. There's a question in the chat window. You cannot see video. Ooh. Unfortunately, I can't help you guys. That's what happens. That's why this is an in-person class. That is unfortunate, the risk that I cannot help you with. That's because of the Zoom issue. So best thing, come to class, attend the lectures in person. So in-person class students, you can see the video, right? And you don't need it. So I had a student who actually was watching the video on the Zoom and in the class. So probably, anyway. So this 2h3 is first row, first column. So this is going to be cosine theta 3 minus sine theta 3, 0, sine theta 3, cosine theta 3, 0, 0, 0, 1, 0, 0, 0. And there will be 1 here. And the last column is going to be the distance between the frame 3 and frame 2. And this distance has to be valid for all possible values of theta 3. Do you agree with me? And that is, what is x distance? So this is the x, this is the y, this is the z. So this is going to be, can someone tell me? a3 cosine theta 3, a3 sine theta 3, and Are you with me? So now let's see what we have to do. I want to find out 0h3. That will give me the position of the end effector with respect to the 0th frame. So this should be 0h1 multiplied by 1h2 multiplied by 2h3. Do you agree with me? So once I perform this computation, I'm gonna get a matrix, and this matrix will have a very interesting structure. This matrix will be something like this. There will be 0R3. 0R3 will be the orientation of the end effector with respect to frame 0. This will give me the orientation. So this guy is orientation of 3 with respect to 0. Here there will be 0, here there will be 1, and this will be px, py, pz. So px is the distance. So px is basically this distance. So this will be px. Py would be this distance. This will be py. And no matter what you do, pz is not going to change. So this will be pz. But all these distances are with respect to this 0th frame. That is super duper important. So this is px is the distance between frame number 3 and frame number 0 along x0. Py is the distance between frame 3 and frame 0 along y0. And pz is the distance between the 0th frame and the 3rd frame along z0. Everyone understood this? No? Okay. You want me to start from the beginning? pz is the distance between the 3rd frame and the 0th frame around z0.
Is it just a position vector?
It's just a position vector. So somebody can say it would be px I0 plus py j0 plus pz k0. Yes.
I might just be understanding the diagram wrong, but it seems like the z position of the end effector could change based on rotation of the first joint or joint 0, and then any combination of rotations in joints 2 or 3.
Really? Oh yeah, basically that would change. Yeah, you are right.
Okay.
So actually what I was trying to do is, okay, you are absolutely right. So basically pz in this particular orientation is a1, but for example, if you have a non-zero values of theta 2 and theta 3, your pz distance would be a1 plus something something.
Okay.
And that's what we will see when we actually use the MATLAB. Okay, so this would be the perfect time to start MATLAB, because I have no intention of doing this calculation by hand. But you are welcome to do that if you guys want. Okay, and since last time I made mistake in typing and talking, I can't do 2 tasks at one time. I already have the typewritten code. and that will save me some embarrassment. Like, hey, yeah, whenever I make mistake, tens. Oh, yeah, that's mistake. That's mistake. That mistake. Okay, all right. So, first, I'm gonna use a symbolic computation, and I wrote the code slightly differently. So I wrote the code in sections so that you have multiple sections to solve. So first line is clear all CLC, and this code is uploaded on Canvas. You are welcome to download that code and follow the way I'm doing it. If not, you are welcome to type it. But turn off your volume controls. Otherwise, there will be ting, ting, ting like background noise. Okay. So first, clear all CLC is going to clear everything. Now I'm going to create symbolic variables A1, A2, A3. They stand for the link lengths. T1, T2, and T3. Those are the joint angles like theta 1, theta 2, theta 3. And then I have THE1, THE2, THE3 that I will use for inverse calculation. And you'll see why I'm doing this. So as far as the forward kinematics is concerned, our variables are A1, A2, A3, T1, T2, T3. Are you with me so far? Now look at 0H1. So 0H1 is cosine theta 1, 0 sine theta 1, sine theta 1, 0 cosine theta 1, 0, 1, 0, A1, 0, 0, 0, 1. Just look at the 0H1 that we derived. Is this correct? 0H1. Is this 0H1 correct? No. Minus, yeah, minus, we also have minus sine theta. I just derived 0H1. Finally. Everyone understands that 0H1 is the same 0H1 I derived 10 minutes ago. Yeah, okay, good. Then 1H2 is cosine theta 2, sine theta 2, minus sine theta 2, A2 cosine theta 2, sine theta 2, cosine theta 2, 0, A2 sine theta 2. Do you agree this is the same? Okay, good. H23, do you see that is the same thing? And if you are too lazy to copy this down, this entire solution is also uploaded on Canvas. Please download that. That way you don't have to. And then confirm. I'm sure there will be somebody who said, I'm so brilliant that I will remember everything at the end of the class. So what I'm going to do is, now I'm going to run the second code, this entire code from here to here. And at the end, I'm going to get 0H3. And this 0H3 is going to be this big matrix, wherein this part, the first 3 by 3 matrix, is going to be the orientation information. And this is Px. Do you agree with me? This is Py. And this is Pz. So you are absolutely correct. Z direction depends upon theta 1. I mean, this is theta 2, theta 2. Okay, so this is the forward kinematics. Everyone clear about the forward kinematics? Please run the code, make sure you are getting the results. I'm sure you'll get the results. So now what I want to do is, I want to actually try to solve this numerically, in a sense that I want to compute. And this exercise is very important, because here is what I'm going to do. I'm going to give some values of link lengths for the robot. For example, my A1 is 135. the distance A1 is 135, A2 is 165, and A3 is 170. So these are the sample values. And can you see Px, Py, Pz is nothing but what I copied from the earlier case. So Px is cosine sine Pz, but only difference here is T1, T2, and T3 are replaced as THE1, THE2, and THE3. The expression is still the same. Now, and there's a reason I did something like this. Because what I do is I do a variable precision arithmetic and do the substitution, a numeric substitution to the symbolic variable. That's why I had to do this. Now, what I'm going to do is I'm going to supply theta1 is equal to 0 degrees. MATLAB does not calculate sine, cosines in degrees. You need to substitute T1, T2, T3 in radians. So 0 degrees is 0 radians. Then T2 is 35 degrees and I convert that into radians. T3 I gave minus 60 and I converted that to radians. Everyone understood this? And what I'm going to do is I'm going to substitute these values A1, A2, A3, T1, T2, T3 into the expression for Px, Py, Pz, and then find out the values of the numerical values of Px, Py, and Pz. Everyone understood this? So substitute A1, A2, A3, T1, T2, T3, get Px, Py, Pz. Yes. There is only one M file.
It ends with the .m extension.
Forward inverse kinematics.m. So this is the file name. Forward underscore and underscore inverse underscore kinematics. So what I would do is I will take this code and run this. And all said and done, this generates a forward kinematics solution. And this forward kinematic solution is Px new is 289, Py new is 0, and Pz new is 157. So what does that mean? That means if my robot has the link length A1 is equal to 135, A2 is equal to 165, A3 is equal to 170, and I set the joint angles, theta 1 is equal to 0, theta 2 is equal to 35, and theta 3 is equal to minus 60, my end effector would be at the position 289, 0, 157. Everyone understood this? This is what is forward kinematics. Yes.
If you use it while actually programming a robot, or like while programming ARM, would you use forward kinematics?
You use it, forward kinematics, inverse kinematics, use all the time.
Which would you use more?
Basically both, because what you do is you generate the equation using forward kinematics and you basically back calculate the theta values based on a simple example. 3D printing. You have a geometry that needs to be 3D printed and you have this gantry. So basically gantry has certain joint values at certain point of time. So you have this CAD model. So basically that CAD model is specifying Px, Py, Pz at every layer, every location. So for each Px, Py, Pz, I need to know what should be my J1, J2, J3. For my next Px, Py, Pz, what should be J1, J2, J3. So I should have the G code that is generated from this CAD geometry. That is exactly how the G code works. So basically you have a CAD model, you have a machining thing, and what you do is based on the geometry, you solve the inverse kinematics problem, and then basically convert that into, I don't know if you have seen the G code. You program that inside the G code and the machine then runs the G code. So machine doesn't know what the part is. Machine only knows these are the joint values. This is the speed at which I need to go. This is the feed and speed I need to supply. That's it. So forward kinematics, inverse kinematics, super important. The next part, velocity analysis, dynamic analysis, controls, again, super duper important. In short, robotics 1, super important. There is no angle at distance. The distance A1, A2, A3 are the lengths. A1 is 135, A2 is 165, A3 is 170. So T1 is the angle theta 1, which is 0 degrees. T2 is the angle, which is 35 degrees. And T3 is the angle, which is minus 60 degrees. And you can change this. And I would encourage you to, let me ask you this. I would encourage you to change this Px, Py, Pz to 1,000, 3,000, 4,000. That clearly, that point is outside the reach of the robot, and see what happens to the solution. Everyone clear about forward kinematics? Okay. Now what I'm going to do is, I'm not going to use these trig identities and this mathematical jugglery to solve inverse kinematics. I'm going to use MATLAB solve function. And this solve function is so smart that it will find out the appropriate trig substitution, appropriate series substitution, appropriate numerical solution to get the solution of this equation. Everyone understood this? The only trick here is, and this is something that you will struggle with, is you have to code those equations correctly inside MATLAB so that solve can solve it for you. That is the trick. So here is what I'm going to recommend. Use this code, that what I have written or what I have given you, as a template. There is a reason I use T1, T2, T3 for forward kinematics, THE1, THE2, THE3 for reverse kinematics, inverse kinematics, because of the VPA substitution. Use this approach, the way I have given this, use this as a skeleton and solve inverse kinematics problem using MATLAB. That will save a lot of headache. Otherwise, if you don't program it the way I have done it over here, MATLAB will not give you a solution, and you will say, hey, the MATLAB doesn't work. No, you have to code the equations correctly so that the solver can find it. Okay, so what I have done, and I'm not going to discuss the syntax because I can't teach you how to swim by demonstrating, right? You have to jump into the water, or I cannot show you a YouTube video of me swimming and then you learn to swim. So what I need you to do is try to play with this code. Use this code to solve inverse kinematic problems that are described in the assignments, and you will get the hang of it. So the first is, I want to find out what is the value of T1, T2, T3. For that, I need to make the substitution. On the left-hand side, I have the symbolic expression, which is Px. On the right-hand side, Px new, Px underscore new is a numerical value. Py is a symbolic expression. On the right-hand side, I have a numeric value. Pz is a symbolic expression. On the right-hand side, I have a numeric value. Are you with me so far? And I'm trying to solve this for the variables THE1, THE2, and THE3. Those are the variables inside the symbolic expression. But the solution of that variable is a numerical solution that needs to be stored in T1, T2, and T3. Everyone understood this? If you mess this sequence up, the MATLAB will not give you a solution. This is all for inverse kinematics. Basically, grab this, run, and boom. Can you see MATLAB is thinking? It is applying all the possible numerical solutions, transformation. Oh, and finally, it gave you the solution. Ta-da! And it gave you 4 solutions, not just one. So what is the first solution? Theta 1 is equal to 0. Theta 2 is equal to minus 25. Theta 3 is equal to 60 degrees. If you substitute these values in your forward kinematics expression, you will get the same Px, Py, Pz. Everyone understood this? Second solution is 180 theta 1, 145 theta 2, 60 degrees theta 3. Still you will get the same value. Third solution is 180 degrees, minus 154 and minus 60. It will still give you the solution. But at the end of the day, this is the value that we substituted for forward kinematics. Our theta 1 was 0 degrees, 35 degrees, and minus 60 degrees. Are you with me so far? So in inverse kinematics, MATLAB gave you multiple solutions. Now, which one to choose? The problem is choice, matrix. Morpheus says Neo. I can give you the red pill or the blue pill. You have red pill, yellow pill, blue pill, and purple pill. So the thing here is what you do is at that point, there are some checks that you can apply. For an example, you can say that I don't want my joint angles to go beyond certain values. So that eliminates some solutions. Or my second solution should be close to the previous solution. That will eliminate some of those solutions. So basically, you can add some if and then type of statements to eliminate out of these 4, you eliminate 3 solutions and then you get the answers. There is a structure here. Essentially, what is happening? For theta 1, there are 2 values, 0 and 180. For theta 1 values of 0, you get 2 values of theta 2. For 180 degrees, you get 2 values of theta 2. And then correspondingly, for this combination, you get 1 value of theta 3, theta 3, theta 3, and theta 3. Are you with me so far? So MATLAB gives you all these solutions in a very nice form. And that's it for inverse kinematics. So next time I will work out problems, forward kinematics, inverse kinematics, same approach. Yeah.
If you ever end up with infinite solutions,
Yeah, in that case, you can actually basically then you will have to again use if and then type of statement to eliminate unwanted solutions. And we'll take those cases. Any questions about the material that we discussed today? Half of the Niku's book is done. Forward kinematics, inverse kinematics. If you want to do velocity, remember the MATLAB command, diff, D-I-F-F. They are done with velocity. All right, I'm going to stop here and I will see you next class.